Hello, everyone. Thank you for joining us, and this should be a really fun one. We'll give some people some time to come in here, but yeah, this is going to be an interesting one. Henri Johnson here, our CEO and founder of FlightScope. Thanks for taking the time.
Thank you, Tyler. And for those that are already joined up, thank you for taking the time as well to join us. I am convinced that you're going to enjoy some of the content. Some of it is, I would say, controversial, but there's science behind it. And I think this will be the first of about three that I will be presenting. I'll go a little bit deeper into the physics on the next presentation. Here, I'm going to show you some interesting things that we did with the FlightScope X3 and then also using a Phantom V12.1. So how are we looking there with the attendance? I think we've got 47 of the 278, so we'll just give a little bit of time for people to sign on and get comfortable, get your cup of coffee, like I have. Or for those that are fortunate to have a nice FlightScope branded thingy.
I didn't bring mine today.
Anyway, so let's see. We've got about 52 people up and alive. We'll give it another minute.
Steve Mike Shy's in here.
Mm-hmm.
Thanks for joining.
Yep. I see some very interesting people on already there. So, and if you have any particular questions, just put it in there. Tyler will moderate the questions and bring it to my attention, and then we'll try to make time to answer that as far as possible. Of course, we are going to have this presentation available afterwards as well if you wanted to view it again, or for those that couldn't log in, they can go in afterwards and see it again.
Yeah, just one thing really quick on the questions. If you all don't mind just asking it in the questions section. We have the chat there on the side, which I can see, but if you can ask it in the actual questions section, that really helps us.
Right, so I think let's make a start.
All right.
Everybody's not on, but we're going to have to make a start now. So I'm going to start sharing the screen here quick. So our presentation today is about the Phantom camera from Vision Research. We own about 5 of them, and one of which is what we call the Phantom, or it's called the Phantom V12.1. And we're going to take a deeper dive into what happens at impact between the club head and the golf ball. Okay, so this was our setup here at Shingle Creek. Firstly, we have Duncan van der Vyver, a very accomplished young golfer. He doesn't give himself a lot of credit, but he's a really good golfer. His brother plays on the South African tour, and Duncan was a student at Mark Immelman at Columbus State University. And when I play with Duncan, for some reason he shoots at least 4 to 7 birdies on the 9. So I think it's pretty good. Anyway, what you'll see there on the left-hand side is the Phantom camera that is put on a tripod, which is kind of an upside-down tripod to keep it off the ground with the lens, and it's focused in on the action. At the back there, you'll see the FlightScope X3. And for those that are interested, you can use the Phantom camera, manually trigger it, but we also have electronics that we developed ourselves that uses the trigger signal from the FlightScope X3, and then it provides a clip for us on the Phantom, and we just have to download it. It still takes a long time to download the footage, especially if you're running at speeds that we've been running at, which I'll show you now. So in this particular case, we run the Phantom V12.1 at 18,000 nominal frames per second, and the image size was set to 640 by 480 pixels. The shutter speed was set to 5 millionths of a second. I'm just going to repeat that. If you think that you heard it wrong, it's not. It's 5 millionths of a second. So for those that are interested, you can do the quick math there in the background. Take a typical club speed of Duncan of about 51 meters per second. We'll work in meters per second. Otherwise, you can go from 113 or 115 miles per hour and work it back from there. But it's easier if you go in meters per second. So say 51 meters per second, and times that by the time to get how far did the club move during the time that the shutter was open, 5 millionths of a second. Maybe somebody do that for us and publish it in the box, then we'll see how close you get to how much the club will move. The second thing that you can do is to see, taking the 640 by 480 pixels, you can actually see how many pixels did the club actually move within the frame during the time that the shutter was open. So what we are trying to do here is to make sure that we hardly get any detectable movement of the club while the shutter is open, okay? The specs of this camera is phenomenal. It's just amazing. I'm just going to put it up here so you can see, if you can read it up there. If it's at full frame at 1280 by 800, it can do 6,242 frames a second. But if you make it like a very small image, which you can select in the software, you can make it 128 by 8 pixels. It can go up to 1 million frames a second. Yeah, you heard me right. 1 million frames a second. That is incredible. But that basically is almost mind-blowing. Why do they do this? These cameras were originally developed, I guess, for military applications, or seeing how something explodes or a bullet goes through something and so on. So we just chose, for the purposes of this one, to run it at about 18,769 frames a second, which is a 640 by 480 resolution. So to give you an idea there. Okay, so let's just quickly go through a few concepts to get the landscape correct. So a rolling shutter, and this is just a very simplistic way of showing it. It doesn't really work like this, but a rolling shutter, say, starts at the top of the sensor, your CCD or CMOS sensor in the camera, and it scans down. It's like a photocopier. It takes one line, one pixel line at a time, and it goes from the top to the bottom. Now, the thing that we wanted to show here is that during a club swing, for instance, if you start at the top and you work your way down in time in line scanning, it's not a stationary process. So you're going to get parts of your image that will be not in sync with what's happened previously. In other words, the whole thing is out of sync. And therefore, you see all kinds of distortions when you use a cell phone. Even the cell phones or cameras that can go at very high frame rates, the frame rate isn't the real thing here. You need to have what we call a global shutter. Now, this is kind of a presentation or representation between the difference between a rolling shutter and a global shutter. So the rolling shutter will start at the top, it'll come down, and the global shutter just takes one flash, and it basically takes all the pixels at the same time. And even so, on a global shutter, the time for which the shutter is open is still a discrete time. So the process can still change, which you are trying to film. So therefore, you need to take into account how much blur do you want to allow in your picture, and that's why you set your shutter speed. And please stop me if I have to explain something a little bit better. And for some of you, this might be old hat, but for some of you, it might be new. I also wanted to just calibrate us in terms of degrees. Now, on a clock watch, if we look, for instance, from 12, we just look 1 minute at a time there. That 1 minute sector, it's a small, very small slice of a pizza, so to speak. That 1 minute represents 6 degrees. there are 360 degrees in a circle, okay? So that shows you how small 6 degrees is. I just wanted to keep that in the back of your head when it comes to direction and face to path and all kinds of things, and the angle of attack. Just keep that in mind, how small that quantity is. This is what it would look like on a club if you are hitting up on a ball by 6 degrees. This is how it would look if you hit up by 1 degree. 1 degree is very small. It's really, really small. And it's super difficult to measure to that accuracy. The validations that we've done, and it took us a long time to validate, I would say that for 98% of all the shots that we measure with the FlightScope X3, our measurements on the D plane normally come to within 1 degree. I would say about 0.7 degrees. And the reason is that the verification systems, even at this kind of level of phantom cameras that we use stereoscopically, it's just extremely difficult to validate things under that kind of quantities. No matter what people say, it is truly difficult. Now let me show you some shots here. Now Duncan hit these driver shots for us, and we have some data there. I'm just going to run it again so you can look at that. And I'm going to run it again, and we're going to talk about it a little bit. Okay, so what I'm going to do now is I'm going to switch over to the Phantom software, and I'm going to show you something here. So I'm going to run it here in the Phantom software, and once it's through, I'm going to come back and stop it at the ball and show you some very interesting things. Okay, now I want to show you this. Okay, that is at impact. I'm just going to zoom in a little bit so you can see. The sun was a little bit behind the clouds today, so we had a little bit of lack of light, but it wasn't too bad. So the first thing I wanted to show you is how long does the ball remain on the club? So, and let me give you the maths here. Our interval between frames, and you can look on the right-hand side there, is 55.55 microseconds, 55.55 millionths of a second between frames. So it's pretty quick. So let's look at, I would say that's contact. Now from contact, we're going to see how long does a ball sit on the club. Let's count them. So 1, 2, 3, 4, 5, 6, 7. There we start seeing a little air. 7, do the math quickly. 7 times 55.55. What does that give you?
Let me get my calculator out.
Come on, Tyler. All right.
388.5.
And that is in microseconds. So basically, let's call it 389. Let's make it 390 microseconds. So the ball remains, this ball remains on this club face for pretty much 390 millionths of a second. So it doesn't stay there very long. But I want to show you something else. I want to show you, let's step through this ball and see how it's compressed. Okay, I'm going to zoom in. It's going to be a little grainy because the light was a little low at the time, but you'll get a pretty good idea of what's happening here. So let's put it there, and I'm going to step through it now. So I'm going to go in there. Now it starts to push on the ball. The ball is being compressed. The ball is starting to move off the tee. You can just see beforehand the ball is still remaining on the tee, although it's compressed. There only it starts to move off the tee. Now it's moving with the club, and it's moving. And look at this. Just before it comes off, it basically reconstitutes pretty quickly. Some of the balls actually form a little balloon behind them, depending on how elastic they are and so on. But it reconstitutes pretty quickly. So I wanted to show you these images. So I'm just going to go back there and just run this again. So this was still a very very good shot from Duncan, and he's very consistent. So I asked Duncan to hit some shots off the sweet spot for our presentation, and it took him a few shots to do that because he's not used to hitting off the sweet spot. But then I have to tell you this little story. It took me a half an hour to get Duncan to hit it off the sweet spot, but at the end of the session, he couldn't hit it on the sweet spot anymore. So if you have anybody that you want to make bad at golf, send them to me. It takes a half an hour, and they're not going to hit the sweet spot often after that.
You might have his number this weekend then.
Yeah. So Duncan, it was funny. He was literally trying to get back on the sweet spot, and it was not intuitive anymore. Anyway, so I also want to point out a few things to you. Look at the shaft reaction as it hits the ball. The shaft wobbles. It just goes like a snake, okay, like a hose pipe almost. You can see a little bit of movement of the head as well, and this was a pretty neat shot, pretty much on the sweep. Okay, so I'm going to close this one, and I'm going to pick up something else for you here. Let me just quickly find that one, which is, let me see. Okay, let me bring that back into better resolution. Aha, look at this. I got Duncan here to totally misbehave. So look at that. So I want to ask then the audience, where was that ball hit? On the face, so to speak. Did you get any answers?
Let's see. Daniel says looks like one of my shots. We have Mr. Prince here, heel, saying heel.
Absolutely.
Low heel.
Yeah, it's heel shot, and the club and the shaft totally misbehaves as a result of that impact. Okay, I'm just gonna pause it here, and I'm gonna go on with the presentation so that I can explain to you what I want to explain here. So let's just go on to some shots. I'm going to sort of quickly run through a few here, and you'll see at the top right there, you'll see the yellow line that was represented by the trajectory top view, and you can see how the club actually, this was a little fade. It was slightly off the sweet spot towards the heel. Let's go to the next one. Now this one, look at that puppy. This is a shot you can't talk to. I mean, they say you can't talk to a hook, but you can't talk to this one either. This thing just slides out with a massive slice to the right, and basically, it's just off the sweet spot towards the heel. Another one here. Okay, let me just go on here a little bit to show you some of the stuff. Okay. Again, that's the heel shot. Okay, I'm just going to go a little bit on. So let's talk about the center of gravity of a golf club and the effects on spin and launch. Okay, so the center of gravity of a golf club could be explained as the balance point of the total club head mass. There are many ways you can describe it, but effectively, I think the easiest to understand it is it's a central balance point of the club. And they say that most of the drivers in the world today, the center of mass, it's literally located within a little box, cube, within inside, and they don't have much room to move it. But any movement of the center of gravity has apparently a massive effect on the outcome of the ball flight. And there's a very specific reason for that. this position of the center of gravity, the balance point in the club, relative to the face, in turn determines the moment of inertia of the club head. Now, there's another term, moment of inertia, okay? Now, the moment of inertia is an acronym that stands for, MOI stands for the moment of inertia. The measurement is grams per centimeter squared normally. It shows you how much resistance a club head has to twisting. The higher the MOI reading, the more resistance it has, the more forgiving the club will play. And this is what the manufacturers are trying to achieve. They're trying to balance the playability of the club versus, the spin and the launch and so on. Pretty interesting mechanics there. Typically, when a golf ball is hit on the toe of the club, the face gets twisted open, okay, because the ball becomes part of the club and it's twisting the face open. That's kind of easy to understand. When it hits the heel, the face gets twisted closed. But counter to what we would think is, we always think that, okay, or golfers think, okay, closed face means maybe it's going to draw for a right-hander. And open face, we think, okay, it's going to fade or slice. Now, exactly the opposite happens when you hit towards the heel. When the face is closing, you hit towards the heel, the face is closing, but the ball slices out of the park. Why does that happen? That's the million-dollar question here. And why does the ball draw or hook when you go towards the toe, and the face opens as a result of the ball being hit on the toe? So, well, the resultant in both cases of the sweet spot means that the ball curves offline, and there is less speed as well because it's less efficient. It's off the sweet spot. But normally the speed is not the big problem. It's the offline that becomes a problem, as we've seen with Duncan's shots. He literally left the fairway with some of those shots. Now, one of the design parameters apparently for a golf club is, Fisher and driver, is a high moment of inertia. Golf club, however, resists that twist and reduces the effect of a miss to some extent. Okay, now let's look at something else here, and this is about momentum. Momentum can be expressed as a product of the club velocity times the club mass. In other words, we can say P equals momentum is mass times velocity. So that gives you, in metric units, SI units, kilogram meters per second. Now, when the ball is struck by a golf club, the ball, let's call it instantaneously, because it's, as you saw with these with the phantom footage, it's microseconds, and that ball becomes part of the club, and it sits there for about less than 400 microseconds. But basically, as soon as the ball comes in contact with the club, it forms, let's call it, part of the club mass. Okay. So that means that the mass of the golf club increases by the addition of the mass of the golf ball. Let's analyze this closer. The driver that we use here was a Ping G410 9-degree. Mass 208 grams or 0.208 kilograms. A typical golf ball mass, approximately 45.93 grams. Or 0.04593 kilograms. And I hope I don't lose you on the physics and maths here. I'm not going to go too deep, don't worry. I'm just going to show you a very interesting point here. So at 113 miles per hour, which Duncan was swinging at, roundabout, or 50.52 meters per second, we can calculate the momentum. Okay, there's a number, 10.51 kilogram meters per second. But after contact with the ball, and the ball is now part of the mass of the club, we have to add the ball mass to the club mass because the mass has increased. Now let's look at what that does. The momentum should remain preserved approximately. I won't get into the details, there are losses, but for the purposes of this discussion, let's just assume that the momentum is pretty much preserved. So the momentum now of the club and the ball together should remain the same, but something's going to change. The mass changed, therefore something else must change. It's going to be the speed of the club. So let's calculate the resultant club velocity when the ball is now part of the club mass. So we use the momentum equation and we just solve for v, for velocity. That's just p over m, the momentum divided by the new mass now, mass being mass of the golf ball plus the golf club. So here we go. We calculated in meters per second and we changed it over to miles per hour, and voila. The speed of the club, let's call it instantaneously changed from 113 miles per hour to 92.6 miles per hour. For all practical purposes. And I'm not going to have an argument here with mathematicians and scientists like myself. Let's call it just, for all practical purposes, instantaneously, the club head mass now which includes the ball mass, has changed from 113 miles per hour to 92.6 miles per hour. So it put on some brakes right there. That's a big difference. That's more than 20 miles per hour that we basically came down in speed with the club head. Now, you saw on the phantom camera for how short time the ball is part of the club head, in other words, in contact with the club head. But even so, it changed the behavior of the club tremendously. The speed just went down by 20 miles per hour like that, within microseconds, within millionths of a second. The speed changed. Okay? Now the question is that the only thing that changed? So the club head mass now travels instantaneously at 92.6 from a pre-collision club speed of 113. Okay, now here's another thing that comes into play. We know that the center of gravity of the club head is enormously important in what happens with the ball. Now, while the ball is part of the club, the entire mass has changed its own balance point because the ball is now added to the mass. And wherever it sits on the club face, it's geometrically also going to change the location of the center of gravity. So the center of gravity of the total mass has changed, the speed has changed. You can imagine there are quite a few things that change. So taking into account that the center of gravity and the moment of inertia of the club head, depending on where the ball was struck on the club face, the momentum vector of the club has therefore also changed. Okay, so while the ball is on the club, things have changed. And we're going to get there, but the question is, where do you want to get your club parameters? Do you want to get it while the ball is part of this club mass? Or do you want to get it somewhere else? It may be argued, therefore, I'll go one back. It may be argued, therefore, that all D-plane parameters are therefore, or could be, let's say could be therefore affected as soon as the ball becomes part of the club head mass. Okay, let's just look at a few things that influence the spin axis of the ball, how it's going to curve. And I'm just going to look now at a few examples. So we show you there a golf ball that's on a toe head, and this is, say, for a right-hand golfer. So that means that the line on the ball there represents pretty much what the spin axis will be doing. A torque force may be explained as the twisting force that's applied to a mass. So you're trying to twist something, and torque, for those that love cars, torque is a beautiful thing. It wants to turn those wheels. It just wants to turn them as quickly as possible, and that gives you that nice feeling of acceleration, which I'm personally in love with. I love a car with torque. That's the best part of it. I don't like speed, but I like torque. That's why I love a Tesla. I don't own one. But anyway, long story short, torque force may be explained as a twisting force applied to a mass. The torque force is applied with a club face on the ball is related to the distance from the location of the club face where the ball was struck to the center of gravity of the club head. In other words, somewhere in the club there's a center of gravity, the balance point. And now depending on where the ball is struck on the face, there's an attempt by this difference between the center of gravity and where the ball is hit on the face. It's like a lever effect. You know what a lever is? Like if you have a balance point and you change the length of the lever, it becomes easier or more difficult depending on where you put the point where you actually lever something. Now, there is a lever or lever effect here as well. And basically, interesting, I don't like the word side spin, but effectively, this is exactly what's trying to happen. If there were, let's say there were no backspin, with a toe hit, and the ball would actually turn this way. So that torque force is actually imparting energy in an actual side spin fashion. Now the beauty of this is that a force vector has magnitude and direction. Okay, this is a little bit of physics, grade 9 physics for you, but we can basically say that the total force applied to the ball is going to be, I'm just going to make it quick. There's a force that's providing the backspin, a torque force, because that's also, by the way, as a result of torque. I'm going to get back to that now. Remind me. The attempted spinning in this direction, the attempted side spin that's produced by the off-center head is another vector quantity. And you can add them like this. The nice thing about vectors, you can add them. They add them in direction and magnitudes. And it's kind of like this. So the top picture there with a little arrow that shows the torque force that's, say, producing the backspin. That's the biggest force happening here. And in terms of the rotation, at least. And then there's a smaller force, which is the off-center head force, which is also a vector one. And you add those two together, and you see that it basically tilts the spin axis to the one side. Okay, if it's too much, don't worry. I just wanted to make sure you understand that there's a torque force that's creating spin, and there's a torque force that's trying to create side spin. And the two together will give you a spin axis. And let's just go on here. Okay. All right, so let's look at this instance where we all want to be on the sweet spot of the club face. I want to ask you now the question and see who's got that right. Why does a golf ball spin backwards anyway? Does anybody want to put a comment there in the chat box, or let's see, why does a ball spin backwards from a golf club? At least for most people. Tyler, does your golf ball, does it spin backwards?
I think it does.
Okay.
Alex says dynamic loft.
Is that it?
That's the only answer we got so far. Let's see.
Okay, I'm gonna have to take a sip of water.
Because the CG, oh, Sorry, now they're coming in. Because the CG of the head is lower than the CG of the ball. Dimples and the defective blow. Spin loft. We all Google.
I try. I'm not going to embarrass anybody or trying to embarrass anybody. I really want us to think about this, because it's like, if you really think about it, why does a ball actually spin backwards? Why doesn't it spin forwards? It's not going to be very good, I can tell you that, but it's not going to fly very well. It's going to go down. It's going to be a dipper. I can hit him. But okay, I'll put it to you simply. And I heard some of the elements in those answers, and thank you guys for throwing in those answers there. As I said, I don't want to embarrass anybody. I really want you to think about it a little bit and try to get on the same page here. So basically, if we look at just the club face normally has some loft, at least. It's not 0 degrees, okay? It's got normally some loft. And yes, there is a center of gravity within the club face, in other words, within the club head. So it's normally a little bit backwards in the club head. Say we're talking about a driver, but for any club, there is a center of gravity. Now, let's look at this the following way. So yes, the ball has got its own center of gravity, which should be pretty much in the center of the ball. Now, there's a difference in the dimension. In other words, if you take the position of the center of gravity of the golf club, and you take the position of the center of gravity of the golf ball, and you look at the dynamic loft, in other words, the actual loft presented at impact, you're going to find that there's a kind of let's call it a slicing effect in this way. Does it make sense? Kind of, it's not a flush, you're actually glancing. There's a bit of a glancing blow as a result of the face angle, but very, very important. Yes, there's a lever effect. There's a torque effect. In other words, the torque force as a result of the difference in dimension from where the center of gravity of the golf ball sits, and thank you for that, and the center of gravity of the golf club, there's a torque force as a result of how the face is sitting, the angle of attack that's happening, by the way, and then there's a torque force that's trying to impart spin in this way. It's predisposed, it's preset to produce backspin. And it's very important in golf to have backspin, because it provides an aerodynamic behavior of the golf ball that gives us a lift force on top of the ball that works a little bit against gravity so that it can drift or fly or glide a little bit further. Otherwise, if there were no spin, that thing is just going to fall out of the air like a cannonball. But it glides a little bit further as a result of the spin. And that's a big balancing point there as well. But let's keep it simple. The spin is also produced as a result of a torque force, and that comes because of the difference in center of gravity between the golf ball and the golf club and in the face. But in a very, very similar way, the torque force that's created, that it comes as a result of where the ball is on the face, left to right or from toe to heel, that torque force is a little bit smaller, but it's also trying to create the spin. It's actually trying to impart side spin, physical side spin. That's the only place where it exists, it appears. Now, you can go deeper, and I don't want to go it now. I'll do that in the next presentation. Because we're already now getting a spin axis, and we haven't even spoken about face to path yet. We've only spoken about wear on the face. And we're already getting shot shape. We're already getting spin axis as a result of wear on the face. And now, hopefully, we understand that the reason that there's a spin axis is a result of the torque force that's trying to impart side rotation, side spin. And that combines with the backspin gives you a tilt axis, okay? We're going to get into the face to path on another one, and that, please join us for the following one, which is coming. We're going to have a lot of fun about the whole story about face to path, the contribution of face, the contribution of path. You are going to love that. It's not as simple as it seems. Anyway, coming back to the sources.
Henry, just a quick note from my side. So, when you were showing the Phantom camera images, so how does the golf ball affect that? So, for instance, let's take the ball that you were using at Shingle, which was, I believe, a tailor-made range ball, correct?
New one, John.
Okay. So, how does that differ from, say, a long drive ball or even a Pro V1?
Okay. So of course, the elasticity of the golf ball is different because of the materials that's used. So there's, they have different layers. These most likely are just two-layer golf balls, two-piece golf balls. But here's the thing: with golf balls these days, people are also trying to optimize the moment of inertia of the golf ball. In other words, its resistance to a force being applied upon it to change direction, in other words, to spin. And here's the thing: they actually distribute the weight differently within the golf ball so that it's got a more or less, so we say, what do you call it, ability to spin. In other words, if you apply a similar force, one ball will spin more than another one because the moment of inertia of the golf ball is different. Okay, so it's by design that they do that. So you'll find that you'll get more spin for some balls than other balls. And it's, you might think that it has to do with the skin more than anything else, but it's not. It's more to do, well, I would say more to do. It's got a lot to do with the moment of inertia of the golf ball itself and how that torque applies to it. Now, what I also would like to debunk is, and I'm going to go back to the Phantom to show you this. So let's look at this shot, which was a pretty bad hit by design. Duncan didn't want to hit it. But you tell me, I'm going to zoom in a little bit here. I want to ask you, can you see how much does this ball slide up the face? Because I've heard this so many times people say, well, you hit the ball at the bottom of the face, it's spinning more. Yeah, it's spinning more. Why? No, because it slides up the face for a longer path. Really? Let's have a look. Contact, full compression, carrying along. How much did that puppy slide up that face? Did you see?
Not very much.
Nah, I don't see anything sliding up, to be quite honest. It might be a millimeter. It's not sliding up the face. The whole face is still available upstairs. It didn't slide up the face. I'm sorry. So if you hit the ball on the bottom of the club, the fact that there's a whole face up there and you think that it's sliding up the face and therefore creating spin, that doesn't seem to be true. That ball is hit and it deforms, and depending on the angle of attack, it's going to deform in a certain way because it depends on how that momentum vector comes into the ball. And there the ball goes, but it didn't really slide up the face. It squashed, or look at that. It's got like a balloon behind it. Do you see that?
Yeah.
It's got and that's before it starts to reconstitute. So yeah, and it didn't slide up the face. So the reason why the ball is spinning more when it's down at the bottom of the club, hitting towards the bottom of the club, is because of the torque force that's there now is trying to help the ball turn this way. So there's an additional torque force as a result of where the ball sits and where the center of gravity of the club sits. So it's trying to impart more spin as a result of a torque force. And in a similar way, if the ball sits to the side, in other words, heel, middle to toe, that same mechanism of torque as a result of the differences in center of gravity, very similar, I would say, for all practical purposes, the same mechanism at work here for a ball going low to high on the face. So let's look at the high on the face thing. Yeah, there's not much above high on the face. It doesn't need it. But the reason why a ball high on the face is spinning less isn't because there's not much room to slide on the golf club. Nope, nope, nope. It's because the torque force is now reversed. There's a force trying to turn it forwards, and that's counteracting the force created as a result of creating the backspin. So I think to me it's pretty clear that there is definitely confusion in the field. Where is my
Yeah, we have some pretty good questions in here if you want to take some of these.
Yes, please do. Let's do.
Okay, so the first one we have here is, how are the cameras connected with the FlightScope? Is there the multicam in use?
Okay, in this case, we don't use the multicam because the Phantom camera is a standalone clip recording system, and it's a few gigabytes per clip, and we just don't have any physical way to really connect that camera into a multicam situation. What we do, however, is we have a piece of electronics done by FlightScope that we connect to the Phantom camera so that the X3 will provide the trigger point. Instead of clicking on the computer monitor, we automate the trigger point, and we have with the Phantom camera what's called a pre-roll and a post-trigger, which basically gives us the video clip. But to get a Phantom image across to, well, the Phantom footage clip over to a computer, that takes a long time. It literally takes 2 minutes to transfer the clip that I've shown you now. Just transferring that with Ethernet. So although we can do it, we just normally don't, because we use this for research and development purposes. If you have the money to buy a Phantom, the smallest Phantoms we've got they're about $40,000. This one, I would think, when it came out, was close to $120,000. I got it for cheaper because I bought it. It was used. But the answer is no. Next question.
Okay, next one we have, does the FlightScope X3 measure the ball data at impact or point of separation?
Okay, let's answer that question quickly for you. So our system, as well as any other Doppler-related tracking systems, have the following in common. We can only see things that move. We don't even see a thing that's standing still, number one. And while the ball, we can see the club moving, and we can see the ball and the club moving there's a little bit of a glitch when that happens because it's so quick. And then as soon as the ball separates from the club, we start measuring it. Now, what we also do in FlightScope is we realize the following, that it's not a good thing to try and measure anything while the ball is on the club. Well, in fact, we can't with the FlightScope measure the exact moment because we don't have that fine sampling time in terms of to find speed points and then angular points during the time, the 400 microseconds, 400 millionths of a second that the ball is on the club. And believe me, if anybody else tells you they can, they can't. At the moment, no system on the market today that I know of, not even in defense, is able to measure with a radar the actual behavior of the ball while it's on the club for that 400 millionths of a second. I'm sorry, it just doesn't happen. Our system, as well as other people out there that has another color system, basically, we have a sampling rate of, say, 40,000 samples a second, but one sample means nothing. We need at least samples for, say, 2,000 microseconds, 2 milliseconds, in order to get one speed point. That's the minimum that you really need. So in other words, if you get one speed point, it means that we have to see the club move for a certain while before we can get a speed point. You can't get speed at a point. You get speed over a distance, because speed by definition is distance over a certain time, distance divided by time. Speed is not an instantaneous measurement, it's an average. It basically gives you the time it took from point A to point B. Doppler just works like this, that you say that in the consumer world has a system that can give you any data of the ball being part of the club. In other words, if you are talking about when full compression is, and let's quickly step through that, that's touch 1, 2, 3, 4, 5, 6, 7. Okay, and then let's go back again. We'll go then 3 in. So touch 1, 2, 3, full compression. So 3 times 55.55. What does that give you? Come, Tyler.
That was 390.
No. 3 times.
3 times.
50. Just to make it 3 times 56.
167.
Okay, that is 167 millionths of a second after impact. No way that any Doppler radar in this world today, in a consumer space or in an industrial space, I'm not talking about defense necessarily, can do this today. Because just the way that it samples, the way that it integrates to get a speed, we use Fourier transforms, FFTs, to get speed, and we need a certain data block in terms of samples. Even if you sample at 100,000 samples a second, it's not going to help you, because you still, the ball, the Doppler that we get from the ball is a certain frequency, the Doppler frequency, and then you have to sample that, and you need, in order to get one period of that signal, you need a certain amount of time. That amount of time is much more than what it takes for the ball to be on the club and off. In other words, we are blind to the time that the ball's on the club. To answer the question, what we do is we will take the speed, say up to that, there, and then we'll take there, and we'll basically do just before impact, because we know when the ball left the club, so we go a little bit back. Just before the ball, just before impact. The club is on the way there. It's not going to change anything. So the one thing I can guarantee you safely is that from about 1 inch out to up to the ball, you cannot do anything. You cannot do anything to change the club at that point. There's nothing you can consciously do to change the behavior of the club over 1 inch. Not at that speed, forget it. So don't worry about it. But what we do is we take the movement vectors of the club just before impact. And this is what you delivered in terms of your club swing. That's what the club is on its way to do. Now, the rest of the physics, basically about the collision, that in its own is absolutely strewn with torque forces depending on where you hit the ball. On the face, what your path is, what your angle of attack is, what your dynamic loft is, and so on. All those things make a huge difference in what the ball is going to do out there. But yeah, we measure the club just before the ball to give you club speed, angle of attack, the path, horizontal swing plane, vertical swing plane, and so on. Then, when the ball starts to leave the club, now there, to there, to there, to there, we have lots of speed points throughout the trajectory. So we've got the ball all the time. Anyway, so there is no practical way to measure the ball while it's on the club. And for anybody to say that they measure the ball at full compression is just a blatant lie, and it's Kool-Aid designed to impress the people out there. It doesn't exist. And even if it existed, that would be the worst thing you do, because as I've shown you, when the ball becomes part of the club mass, instantaneously the speed of the club, in this case, changed by 20 miles per hour, and that's not the only thing that changed. The behavior of that mass in total has changed. Full stop. Okay, so any other questions there?
Yeah, we have another one here. Does FlightScope ultimately use Phantom to test and verify all data parameters?
Yeah, as far as we can. We've got 5 of them. We also have a full cage of instrumented machine vision cameras that we use with, flashing LEDs and all kinds of stuff that we put onto the club, off the club, and then we also outside we have fusion systems that we actually use cameras with radar to track the ball until it lands and also what it rolls. We do a lot of verification, and man, it takes time. It's a very tedious process.
Yeah. Just one question here from Robert. I think he missed it, but how many samples per second does FlightScope use? I think you mentioned it earlier.
Yeah. And I want to make it clear for you. Samples per second and data points per second are different things. Because in engineering terms, we are sampling the Doppler frequencies, say at 40 kilohertz, 40,000 samples a second, say. And I think our friends in other countries do the same thing, okay? Pretty much, depending on whether you're working in X-band or in K-band. But the Doppler frequency determines basically what sampling frequency you're going to have. But then you get a data point out, which is like every 2,000th of a second. Does that make sense? So you're not going to get it out quicker than every 2,000th of a second. We actually can slide our FFT, so we can actually, have it closer. But still, your data block, you need a certain number of samples, raw samples, in order to get an FFT, fast Fourier transform result, to get your speed from which you get, or your angle differences and so on. So it can be confusing when people say to you, "Oh, we sample at 40,000 samples a second." Hey, those are not usable data points in terms of actual speed points or angular points, because they still needs to be converted into a speed point, an angle point, and so on. And that basically you would have, say, maybe if you have a very small FFT block, say 64 points, or 128, or 256, or 512, 1024, it takes certain time. So you need a certain number of samples. So typically, you would use, say, 256 points of the 40,000 samples per second. So suddenly your 40,000 samples per second are divided by 256. So you basically get the idea. So not us, not our competitor, actually use more or less than about, I would say, 2 millisecond, 2 millisecond intervals.
All right.
Okay, so these are just some, show you some pictures of the golf ball, sitting high, sitting low, to give you an idea that, again, center of gravity of the golf ball, center of gravity of the club, different, and therefore there are torque forces involved. And again, please remember that it's not because the ball slides on the face that you're getting spin. Nope. It's because of torque forces. All right. I think we just ran out of time, but this is chapter 1, and stay tuned. We're going to have some very interesting things for you in the future. Following up on this, and the very next one will be about the actual contribution of phase to path and phase in terms of direction. Let's put it this way: what contribution does phase angle have for direction for a driver, iron, and so on? And then the phase to path relationship, how does that work in terms of producing the curvature? We are going to give you some practical examples, and we're going to take a variety of clubs to show you some interesting things that will also debunk some of the stuff that's out in the industry that people believe blindly. I want to end off by this, that if you are using a FlightScope or any other technology, and you are bent on using the D-plane, face to path, and that kind of stuff, please remember the following. As a scientist, I want to encourage you to make your students hit the sweet spot first before you get into the deep lane. If you're off the deep lane, you're in troubled water. That's it. It's muddy. It's really muddy for all kinds of purposes. You're going to have a bad outcome on the golf course, number one. And secondly, it's not going to make sense to you because the deep lane formulas don't work off the sweet spot. Full stop. The torque forces involved are just overwhelming. You cannot use deep lane effectively off the sweet spot. You can't play golf effectively off the sweet spot. Ask Duncan, great golfer. He battled to get back on the sweet spot. So I would suggest the following. Like you can teach somebody to stand with his or her knees on a balance ball. It takes time for those that haven't done it, but you can. Learn how to hit the sweet spot. Teach your students how to hit the sweet spot first. And that should be you shouldn't deviate from that. That should be a first objective, and then you can start looking at the deep lane. Thank you very much all for attending. I hope you enjoyed it, and give us feedback, and I hope it meant something for you. We'll be back.
Yeah, thank you. If we didn't get to your question, also just know we'll be sending you an email with an answer. So just be on the lookout for that. Thank you.
Bye-bye.
Bye-bye.